And I think it's quite a good tool to go a bit beyond of the outcomes we have when we do experiments in the field. And I would like to show you some examples, and I will focus on abiotic resources and traits. Well, the motivation, maybe we can keep it short, because you know that there are advantages of intercropping over monoculture. And there are some difficulties we still have, which is, for instance, the finding the appropriate partner combination of species, but also of cultivars, or we can also call them idiotypes, but also the appropriate management from field design to fertilization. And so these interactions in the system are very complicated. Usually in monocultures, we have to do with G times E times M interactions. So you know the term, right? G, genotype, E, environment,
Sure,
M, management. And in intercropping, we have one additional G, which makes it much more complicated. And so models can help us to interpret the data we have, but they also can help us to better understand what is happening in the field, and they can also help us to look a bit beyond what we find in the experiment. And I have it phrased a bit differently, the motivation, because this is how we usually say it after field experiments. After 2 years of field experiments, we say, okay, now we have a yield decline, but was it actually the water, or was it the nitrogen, or the phosphorus, or was it both? We don't know. Or we have the question, we're angry about ourselves because we haven't measured soil moisture. Yeah, it would have been so important, but nobody thought about it. We had no budget. And then the classical one, which always appears, we have 2 years of data, that's nice, but we actually need 1 or 2 more years, because we need a wet season, and also we have only loamy sites, but we have no sandy sites. Yeah, you can, and this is what always happens. And I think models can help us out of these problems, at least a bit. And what you will learn in the next 30 to 45 minutes, if you stay awake. First of all, I will give you a few examples of which research questions arise in field experiments, and I will base that on our real experiments we do and on the real questions we have. I will explain what process-based models are, and then I will show you how they can be applied to interpret experimental results, to better understand interactions and intercropping, to fill data gaps, or to simulate not measured variables. But also, how can we use models to look beyond? So how can we use them to find where and under which conditions intercropping may perform well, so upscaling or regionalization. And so first of all, I will show you 2 experiments, or explain you shortly 2 experiments where our research questions are based on, or the later research questions here are based on. Then I will tell you what process-based models are. And then we will go through this 3 research questions. Can we use models to interpret experiments and disentangle complex interactions? Are there further ecosystem services that are fostered by intercropping? And can we use models for upscaling? So first, I'll come to this one. And I will not say so much, because Madhuri already explained the experiment quite nicely. So I'm a colleague of Madhuri, and I was involved in her experiment. And so this experiment here we conducted in 4 environments, and we grew fava bean and spring wheat, and we tested 10 different spring wheat cultivars and 2 different fava bean cultivars in a substitutive intercropping design. And we had a hypothesis. The hypothesis was spring wheat height affects mixture performance. And we thought, actually, the good thing is that it wasn't us, because it was the bosses that thought the hypothesis of them. we would have done it differently, right? So the bosses, they thought that the key trait is the plant height of the cereal. And what we find out, or we saw, and I'm sure what we has shown it, is that there's a weak correlation between the grain yield in the mixture and the spring height. But obviously, it's quite a cloudy thing. Yeah? So maybe it was not the key trait. Sorry, wrong direction. Okay, so to keep it short, yeah, our key insights were that actually the very early, the species interact actually at a very early stage, which I couldn't believe at the beginning, to be honest, but now I'm convinced it's really like that. And also in the PhD thesis of Euro's PhD candidate, she saw the same. And this has a legacy effect. So this very early, shortly after emergence already, at least in this full mixture, in this full mixture, we have a legacy effect. And if you have an early dominance of the serial partner, he or she gets stronger and stronger and suppresses more and more the legume. And then we also find out that there is a very difficult interaction, and the cultivar was actually not the main explanatory, did not give them most of the explanations, but it was rather the environment and also the sowing density. I forgot to say that we had tested 2 sowing densities, right? And so to keep it short, it was very complex, and very complex to find an overall pattern also, and even if we have conducted such a complicated experiment. So what is actually left over is the key question: what is actually the crop trait that is most relevant, or which crop traits are most relevant, which drove the performance for different environments? Because in one environment, maybe this cultivar performed well, but in the other environment, it did not. And what are the effects of management and environment? Then, so I'm also a very biased researcher. I love roots. And we did also some root observations. We took root course for meter depth. This was actually done by Philip, so he has nice memories of that experience. And then we cut them into pieces, and then we washed off the soil, sieved the soil, or sieved the leftover the roots, and then we scanned them, a flatbed scanner, and then we used, which is actually done by colleagues in Wageningen, we used FT spectroscopy to differentiate between the 2 species. So because you have this is a good example. In that case, I think there are 2 different roots of 2 different species, but in the field it's very much more difficult to distinguish between species. But you have 2 to do that, and one of them is this FT spectroscopy. And to keep it a bit condensed, so what we found out is actually that the sowing density had a high impact on the rooting, and the lower sowing density fostered a deeper rooting. Because when you had a very dense canopy, the plants compete a lot for light, and they invest a lot of carbon into the growth, not so much in the roots. But when they have a bit more space, they also grew deeper. And so the sowing density was more important than the spring wheat cultivar. And then we also identified wheat traits that were beneficial in intercropping, which was actually this the root elongation at the very early beginning. So if you have a cereal that grows very much at the beginning, it dominates strongly over the legume, also in the later season. And then you get in the end a lower LER, because correct me if I'm wrong, but very important for the LER is to have a strong weak partner. If the cereal suppresses the legume, you also get a low LER usually. So if you have to get also some good yield of the legume to have an overall well LER. And if you have a cereal that is very strong at the beginning, it's not beneficial for the final LER. So the question that still is open for us is which root trait partners should be combined. So how do we have to combine them to get a good overall beneficial intercropping system? And I'll come to the next project. This is the one Jochen has already mentioned. Also, Bokke is a partner in the project. So it's a project of 27 partners. Many of them are from Europe. There are also some from China, like Nilong, who will talk later today, yes. And some from Africa. And so it's I don't want to go into details about the, also you're from the project, sorry, exactly. So I don't want to go so much into detail. Also, you will get a talk more tomorrow about that. But it's not only on like doing experiments on intercropping, but it's also about the whole value chain, the societal demand, the market, the lock-ins, and then also about potential services and disservices of intercropping beyond yield. And what we do for that is, in one part of that project is to have common field experiments, classical field on-station field experiments, where we decided to have cereal and legumes, and we have key treatments that everybody does or conducts, and then we will have a meta-analysis also on the data finally. And some of them measure also the laughing gas emissions or nitrous oxide emissions, which is a very strong greenhouse gas. And those countries are marked in this darkish green. This is a disservice, obviously. No? So we are one of the partners that conduct one of these experiments, and we were quite over-motivated, so we do a lot of measurements. We have, again, the same species, fava bean and spring wheat, and we did it by purpose because we selected 2 cultivars that we identified as being quite different in performance. So one of the cultivars that performed well in under dry conditions and one that performed well under wet conditions. And so this is what I meant with the pre-selection from root dry. And then we're measuring like standard root rates you measure, then soil water potential and soil water content. And then we measure the gases and emissions. This is here as shown here in that picture. We have this fancy box on wheels, and there is a spectrometer in it, also a FTS spectrometer. And you can see here 4 plastic tubes that are installed in the soil at 10 centimeter deep. And then you go there, and then you put caps on them. As you see here, 4 caps. They are connected with each other, and with the FTS spectrometer, and measures in situ the gases. CO2, methane, and laughing gas. Then you stay there for 10 minutes, and then you see increase or decrease or nothing. And then you remove the caps, and then you go to the next point. And then we also measure leaching, nitrate leaching, with the suction caps that suck out the leachate, and then you collect it in the bottle, and then whenever the bottle is kind of full, so every 1 or 2 weeks, depending on. In summer, maybe every 3 or 4 weeks. In winter, every week, you get the nitrate and the volume of the water to get the nitrate leaching at a certain depth.
How deep do you go for leaching?
So we went only until 60 centimeters. So it's not. It's a good point. We cannot really call it leaching. It's the nitrate at a certain depth.
Yeah, that's still the root zone.
It's still the root zone. That's true.
Yeah.
Unless it's winter.
Yes.
Then, if you have a winter, we have very high rainfalls.
Yeah.
All of this will be lost.
Yes.
Exactly. So it's actually extractable nitrate, but to keep it short, I call it enriching. So my question is actually, what do you think? What will be? Do you expect nitrate emissions in the monocrops? In which monocrop? In which intercrop? And where do you expect nitrate leaching? What are your expectations? Well, we have different fertilizer treatments also, but here 70 kilogram in the spring wheat and half of it in the mixture.
Okay.
I will expect monocropping of the species that have shallow but consistent to have higher leaching.
Which is the one with the shallow roots?
I don't know, but the one of these. I don't know what it means.
Do you know how the root system of fava bean looks like?
Yeah.
I
mean, I have seen it.
The taproot. It's a taproot.
I've never seen it.
Yeah. So I have also not really very good answers for all my questions I ask you. So you can just say whatever you think. But so it has a taproot this time, I'm certain. And also sometimes you read and you see that it grows very deep, and sometimes it doesn't. So it's very difficult to say if it's shallow or deep rooting, because also it's very sensitive with compacted soil layers. And we have here, this is a para-brown erde. What's that in English? Para-brown earth. Well, it's a alluvial soil, and you have a layer with a higher clay content. Actually, it's not really very high, and the weeds don't care at all. But this cover bean is really super susceptible to any compaction. Whenever it reaches this layer, it stops. So it really depends. But in general, I would say the faba bean is more shallow rooting than the spring. But actually, I wanted you to talk and not me. So what do you expect?
So in monoculture, you add double of the fertilizer than the intercropping.
We add 70 kilogram in the spring wheat, none in the faba bean, and half, 35 kilos, in the intercrop.
Yeah.
But then how you are going to compare the leaching? How do you know that the monoculture is more leaching because you add just more fertilizer? How you are going to compare it?
No, because why? You have half of the fertilizer also in the intercropping.
And in monoculture, it's a double.
Yeah, but only in the spring wheat, and not in the faba bean. The faba bean you don't apply N.
So your system is fully mixed, or it's in strips?
It's fully mixed.
It's fully mixed. Yeah. So it's a very logical approach. If you give 70 kilogram to soil wheat, you give nothing to faba, and then you mix them up totally. You give the average. It's not more. It's not less. It's the same. So I think you have to compare expected leaching to actual leaching. And the expected would be the average of the soil drops.
Yeah, exactly.
So that's a totally fair expectation.
But also one-on-one substitute. You replace it one-on-one in the
Exactly.
Okay.
Yeah. Do you think that there are emissions, NTO emissions after a legume?
I think Bowen knows that.
Yeah.
Yeah. So what's your answer?
It depends.
No.
Sorry.
He didn't get the question.
Yeah. Okay.
So they have 70 kilogram of nitrogen applied in wheat. No 9 kilogram nitrogen applied in faba bean.
Yeah.
Then they have a 50 full mixture applied.
Yeah.
35 kilogram of nitrogen.
Yeah.
So among the three treatments, which one has the most N2O emission? You're expert.
My experiment, the solar means.
No, okay, for her experiment. Wheat and faba bean.
I think for wheat gets the higher intelligence.
Okay.
Yes.
Because it's fertilized, maybe you mean.
I mean the fertilizer is higher in the strip of wheat. Yeah, I think also for the faba bean, yes, for the lower natural packaging rates, and also I think
Yeah, I think it's very difficult, and to be honest, I have no clear hypothesis myself, because on the one hand, you put mineral fertilizer on the wheat, that means emission. Yeah, on the other hand, the legume has very high N concentration in the roots. And if you look not only at the growth period, but also at the legacy, in autumn, you have a very narrow CN ratio, and you have a lot of root residues. There must be emissions, right?
emissions come from denitrifying here.
Denitrification, and most,
Yeah. So
and from nitrification.
Yeah, so the process is you have free nitrates in the soil, and I think it needs to become anoxic, and then you get N2O emission. So my prediction would be a lot more in the wheat, because you have this free nitrate in the soil solution, and the wheat is simply not quick enough to take it out. So immediately after fertilizer application, I would expect a spike in
Exactly.
in N2O emission. That's what I would expect, and I would expect it less in the mixture, because fava bean also loves nitrogen, so they have no trouble taking up nitrogen.
Exactly.
But
There is
it's-
enough.
Professor Mathieu was also meaning that if you, in one system you apply fertilizer, in one system not. So then it's logical, if what you say is true, that one treatment has a spike in N2O emission because you apply the fertilizer. That's-
More fertile, double
more-
fertile.
Yeah, that's difficult to compare the emissions, right? Because the emissions are a product
No.
from the fertilizer you add.
No, it's easy to compare the emissions. It can be.
Because the
This
one
is
system
interesting.
where they apply double of fertilizer, the amount of spring wheat also double there. That's why it's a fair comparison.
Okay.
The other system, the spring wheat is or wheat is also half.
So I'm afraid I have 150 slides left. So we will, no, I'm kidding. We will continue, but I think the discussion is also good to have a hypothesis, and it's not clear. But maybe to finish this, when N2O emissions you have when you have application of mineral fertilizer, usually you have a peak afterwards. Then you have it when you have saturated soil. The pores are full, bloop, comes out, right? And when you have tillage. Yeah. And I will show you now the results for the first year. So I'm not saying that this is representative, mainly because all of you were wrong. So it could also be that in the end it's different, right? So it's just the very first, and it's only the season, what you see here. And Joanne was highest in the fava bean. And then you have here, this is the spring wheat cultivar 1 and spring wheat cultivar 2 sole cropping. And this is the mixture. So you had the lowest emissions in the mixture. But again, I don't want to generalize that. Yeah? But also what I find very interesting is that you have a very strong cultivar effect, right? It makes a high difference if you have this cultivar or if you have that cultivar.
Which cultivar you used again?
Suahab and Annabelle
And fava bean.
and Fanfare.
Do you know what's the mechanism of the biological reason that there's difference between the cultivars?
So as a biased researcher, I think the roots have a very high impact. Well, no, I cannot give you at the end a list that I think this and this and this trait matter, and you have to compare it like that, then it's fine. Yeah, I just want to show you how we can maybe narrow it down, but this is definitely something that we identify. I mean, this the emissions of the first season. The season starts. Usually you have the emission at the beginning because you have the fertilization early, and then it gets dry. When it's dry, you have no emissions. So the early growth also matters here. And I think the early growth has a lot to do with the roots also. So I can explain it is my bias. Okay, we have these emissions, and they were lower in the intercropping, at least here. But what is actually much more interesting, or at least as interesting as the legacy effect. So what happens in autumn? You have a lot of fava bean roots left with very high N concentration, 2% of N. And what happens in winter is I expect this to be even higher. And well, then also here. But we will see. Maybe then I can say the 2 years come. And
So here we don't see the seasonal trend, but
no, it's just the cumulative one.
But is it so that in the wheat it's more close to the fertilizer application?
Yes.
In the fava bean it's in the autumn when the roots are decaying, it's wet and.
This is only during the season. Unfortunately, now what I have here, it's only during the
How long
season.
is the season? Until
End of July.
oh, that's certainly surprising.
Yeah, absolutely, it is.
Yeah, totally surprising.
Okay, then I promised to show a lot of equations. No, this one you already know, right? The PLER. And I want to focus here again on something. So this is the one cultivar Annabelle, and this is the LER of the other cultivar Suahab. And I told you that we had 3 fertilizer treatments, but so we had a very rainy spring, and then we could sow finally, and then we had no rain drop at all for a long time. So the kernels of the fertilizer lay on the ground for weeks. Yeah? So this is also why we have no significant effect of the N fertilization treatment here. We may see it then, okay, of course, in the NTO emissions, but not here. And this is why let's ignore now the details here. But what you see here is that one of the cultivars has a positive, has a LER above 1, and the other one has below 1. And this is why we selected these two, because they always behave like that. This year, this is better, the other year, that one is better. So we try to find with these two contrasting cultivars to find out what actually the trait is that makes the difference. And so this is another question we have. So which trait drives the performance? So now that you know what research questions drive us, I would like to explain you a bit what process-based models are. So first of all, definition, process-based crop simulation models are dynamic software tools that simulate the crop development and the growth in relation to the environmental conditions like the weather data and the soil characteristics and management practices like sowing, fertilizer application, based on agronomic principles. I'll come to that in a bit. Here are some examples of processes. So first of all, maybe to distinguish this kind of model to what Jochen will explain later, it's a 1D model, so it simulates, let's say, one homogeneous field or one homogeneous plot. So there are no interactions, no vertical, horizontal water flow or so. It's a 1D column. And to run the model, you need weather data of that site, the soil properties, then you need some information about the cultivar and the management. It simulates processes like the light interception and utilization, root distribution, evapotranspiration, and soil water and soil nitrogen dynamics, nutrient dynamics, but mainly nitrogen. And then the good thing is that you get a lot of outputs that are hard, or some of them are hard to measure. As part of the IPCC report. And so what do I mean with agronomic principles? So these models consist of a large number of equations. All of them are usually mathematically not difficult. And there are correlations usually based on agronomic principles, like this one, net photosynthesis over irradiance, or maximum gross photosynthesis over temperature for C3 and C4 plants. So we have like biological knowledge brought into equations, and these equations are connected to each other and build up the model. And it's not only economic principles, but also hydrological principles like a water retention curve, or from soil science like soil organic carbon turnover pools. So this is how the models look like. And I just show this one example to give you a feeling about how exact they are, what they can calculate. So it's the calculation of the total daily biomass increase, which is calculated as the light crop-specific light use efficiency. So it depends on the crop. Light use efficiency of the crops differ, of course, but it may also depend a bit on the cultivar. So there could be also some differences between cultivars, multiplied by the intercepted photosynthetic active radiation. This is the simple formula. And this is a parameter, and this is a crop-specific parameter, and this is then itself depends on the incoming radiation measured by the weather station, and extinction coefficient, that is again a parameter, and the leaf area index, which is again calculated. And the daily biomass accumulation considers or can be limited by stresses or by limitations. This could be drought stress, this can be nutrient deficiency. Most models consider N only and by temperature, heat and cold temperature. Yeah.
So if you have a new crop and you first have to, the laboratory or the greenhouse, determine these two parameters.
Yeah, so usually you have a model and then you have default parameter sets for, let's say, common winter wheat in Central Europe, a common potato in Germany also. And from that, usually you can calibrate it to fit to your specific cultivar. If you have a new crop, that's actually quite complicated because you have quite a lot of parameters. And some of them you can measure, but some of them are not directly measurable actually. So this is a lot of work if you have a new species. Okay, so you have stresses, and then the dominant stress of these three reduces the potential increase. And then you have a potential increase of X gram per square meter, and this is then allocated, this dry matter is then allocated into different organs. And this allocation is done by a table. So this is also one of the parameters, a table at that development stage. So much goes to the roots, so much goes to the leaves, so much goes to the stems. Yeah? Okay, if you want to run a model to create a virtual feed for your site, as I said, you need crop parameters, you need the soil information, weather information, and you need management information. And we have now created or developed an intercrop model, which is quasi 2D, let's say. And the model considers, so it has the crops share one soil because we have a full mixture. We have two crops with a simplified architecture. And we, of course, share one atmosphere. And the model considers the growth of two species. It considers soil water dynamics and N dynamics. It also considers biological N fixation of the legume. That means the plants can compete for radiation because they have a different height, or they can have a different height, and then they compete for radiation. And then they can also compete for soil, water, and nitrogen. This depends on the root length density and a specific layer. So the soil can be discretized, for instance, in 5 centimeter layers, so 0 to 5, 5 to 10, and so on. And if crop 1 has a root length density of 5 in one layer, and crop 2 has a root length density of 10, then the one with 10 can take up 2 times more water and N. It's just proportional, yeah. Depends also, of course, on the demand and the availability. So we can simulate complementarity and compensation, but the model does not consider weeds, it does not consider pests, diseases, and it also does not consider facilitation, exudates, yeah. So it has definitely some limitations, but for light soil, water, and soil, and it works quite well. Okay. So we have used that data set from Maduri for calibration of the model. We used all kinds of data we had, so not only yield, but also biomass cards. We measured power, we measured height, we had this bit of root measurements. So we used all the data we had. And here you can see for the 3 environments, here are 3 environments on the x-axis. This is fava bean in intercrop, this is spring wheat in intercrop. This shows you actually the validation, the grain yield in blue is simulated and green is observed. So you can see that there is quite a good fit of the observed with the simulated value. But we have here a bit of a problem on the observed values at this environment are a bit lower, but this can be explained because it's the organic side and we had some weed infestation, which is not considered by the model, and that's why it overestimates the yield. Also here the LER, again here observed and simulated for one environment, second and third environment, and here is the one line, so you can see that it's maybe not always perfectly met, but it shows the dynamics. And I think it's also not the overall aim to always perfectly meet or simulate something, because also observations are usually not perfect. I mean, if you look at the standard deviations for the measurements, you have to accept also some deviations from the modeling results from the measurements. Okay, now I will come to the third part. how can we use models to interpret experimental results and better understand complex interactions. First of all, I will come to one example where this, which is around the simulated, we can simulate variables that we cannot or we did not measure. And this is actually I'm answering the research question Bobke had. No, that's a bit. It's about water uptake.
Okay.
So
You try.
you should listen carefully now. So I have to explain it a bit because it's important that you understand it. So this is the accumulated simulated crop water uptake. Each of the bars. This is here the average of the mono. So it's the expected water uptake, half of the monocrops, half of each monocrop. And this is the simulated uptake in the mixture. Huh? This is for the spring wheat in the monocrop, and this is spring wheat in the mixtures. Fava bean in the monocrop, fava bean in the mixture. And the colors are the soil layers. So blue is topsoil, 0 to 30, then green is 30 to 60, blue is 60 to 90, and orange is then 90 to 120 meters, centimeters. And what we see here is that the absolute water uptake is actually the same in cropping and monoculture, at least in this experiment.
Yes.
Huh?
In the simulation.
In the simulation,
Yeah.
yeah. But we have also measurements of the soil water content, which we compared with the simulations.
Yes.
Yeah. So we had some. I mean, it's very hard to measure water uptake in crops. We can measure sap flow, but you will never ever, unless with isotopes, find out from which layer. So I think it's, of course, it's a simplification. Yeah. But measuring it is really hell. So sap flow and isotopes.
Sap flow is fun.
Okay. I can give you our device if you want. Yeah, it's fun. That's depends.
Yeah, it's fun. I like it also.
Yeah. I remind you the next time at midnight on the field.
Hell. Why is it hell?
Yeah. Ask Philip how many nights he stayed with that device.
Yeah, it's really complicated to install it, but if you install it already, then you get lots of good data and it's already working. Maybe you have to change one sensor or something, but it's really interesting to see maybe. And for this measurement that we already took, it's really nice additional information.
We can discuss it when there's time. So.
Yeah. Okay. Okay, so what you see here, that the overall uptake, total uptake was not higher, but what we see is that the spring wheat took up more water in the mixture as compared when it grew in the monoculture. And this happened especially in the deeper soil layers, 30 to 90, 90 to 120. And this led then, of course, to less water left over for the fava bean. So it is more it's not the overall uptake, but it is the distribution or partitioning between the crops that makes a difference. Now let's come to N, and here it gets a bit more complicated because we have a vacuum that also fixates atmospheric nitrogen. Similar figure, average, so expected N uptake from the soil plus N fixation, and here in the mixture, the N fixation is the dark blue part, and this is the uptake. And what we find here is that the intercropping reduced the absolute biological. In intercropping, the absolute biological N fixation is actually lower than in the mono. Do you have an explanation for that? So in the mixture, the total biological N fixation is lower than in the expected.
What than the expected?
Than in the expected. Yeah.
Oh.
Mm-hmm. Yeah.
Yeah, because the fava bean get also fertilized, and
The fava bean.
yeah, in the mixture.
Yeah. Okay.
Yeah.
So
And if some nitrogen is available, the N fixation rate decreases.
So the fava bean also takes up fertilizer,
Yeah.
So it gets lazy. Yeah.
Mm.
And the other explanation is that there are also less fava beans in the mixture because it's suppressed by the cereal.
It's actually is surprisingly a lot.
Yeah, surprisingly a lot.
Yeah, half the plants and even they're fertilized, they still have almost the same fixation and simulation. I'm curious about the data.
Yeah, we can have a look.
Yeah, yeah.
And exactly, yeah. But what happened? So this is a mean over 3 environments, whereas this is just one environment. But the spring wheat N uptake increased by 44%. Right, this is what we expect. Right, this is also where we do intercropping with cereals and legumes. We increase the N uptake from the spring wheat.
So it increased compared. So there's this monoculture mean. What does
So the
it mean?
spring and
40%
the
more
spring.
than what?
Then in the expected, monoculture, it took up 44% more than in the mixture.
I'm the only one that understands them.
So this is the average of the 2 monocrops, because we have a 1-by-1 substituted design,
Yes.
right? So this is the
Yes.
expected
Yes.
N uptake and fixation and N uptake, and it is 44% higher compared to the mixture. So this is not the graph that fits to that number because it's just one environment. Yeah? So I compare this bar with this bar here. Yeah?
Okay.
Oh,
So this bar is 44% lower than this bar if you look at the 3 environments.
Yeah. Okay.
Okay. Okay, then so okay. Now I'm coming again. I'm switching again back to water, and we have talked about cumulative uptakes, and now I want to zoom into daily data, because the advantage of the model is that you can have daily output and you can look at the different development stages. And so if we look at the experimental data, not the simulations and observations, what we found is that the early wheat rooting dominance negatively impacted the fava bean. And we found also that the root growth in the deeper soil layers was dominated by competition. So in the above ground, there was a lot of complementarity, but in the below ground, there was a lot of competition between the roots. And this is something we not only observed, but we also simulated. And what was most critical for the fava bean, so fava bean is quite susceptible to drought stress, and the most critical phase for that in our environments was the very early stage, but also the period before and around flowering. And this can be also visualized with the model. So this is now one of the experiments. This is the day after sowing on the x-axis, and this is just a factor, the daily transpiration reduction factor. That means if it's 1, that means no drought stress, and if it's 0, a lot of drought stress. And what you can see here in blue is this factor for sole cropping, fava bean in sole crop, and in green you see it for fava bean in the mixture. And you can see that especially here at the very beginning, the fava bean in the mixture experienced drought. And it did again experience drought here in that period, which was around flowering. So you can so with the model, you can also identify which periods are critical. And then something which I have now no data to convince you, but what we have found out also is that the resource acquisition is more relevant than the resource use efficiency. So the crops don't get more efficient, like they don't take up less water and get higher yield, or less water and get the same yield. But what they mainly do is they get better access to the resources and partition them between the species. So it's more that they can acquire better the resources, then they get more resource use efficient. I want to show you one way to visualize the data from intercropping, which I find quite interesting. This is from Eric Schüst. It's the so-called C4 approach. He has published a paper on that. And you plot the PLER of fava bean against the PLER of spring wheat, and then you have these four boxes. And when the values are in that box, it means the legume suppresses a cereal. In that box, it means the cereal suppresses the legume. Here, complementarity and cooperation are stronger than competition, and here the competition dominates. And so what we are doing most of the time is that we want to prove that our model is accurate, not only with absolute values, but also with values or interpretations. Yeah, and so this is why we have also plotted our simulations against the observations. So the circles and everything that is in black is simulated. So we have the three environments here with this form of the box. So this is one environment, this is one environment, and this is one environment. And simulated has a black border, and observed has a red border. So I mean, they are kind of close, maybe not here so much, but most of the time they are also in the same category. So they here simulations and observations both prove or show that complementarity and cooperation are strong. And here, well, maybe beside this one, but here also models and observations both show that the cereal suppresses the legume. Yeah.
Do you expect that you see the different densities of the simulation clustered together, and not, for example, for the Altendorf 2021, the simulations cluster more closely together than the so the densities of simulator more close together, and the observations, the density are more close together, and not another pair of the density simulated and observed of the circles, for example. As perhaps very,
these are the two densities together, and these are the two densities together.
Would you more expect that the, for example, the high density that the observed and simulated are closer together than that the?
Yeah. So what you see here is that the model has problems to simulate density effects. Yeah, that is true. Yeah. And then what you can also see here, that we have this difference between on that side, which is the organic side, which has the wheat problem. So if you have a deep look at the data, you also see where the problems are, either from the observations or from the modeling approach. Exactly. So this is what you can do with your yield data, let's say, or your biomass data or whatever. I think it's quite a nice way to also understand the data, plotted this way, but you can also, but the question is then still, what is the driving resource, or why and when is it happening? And what we did here is also, you can also plot the PLERs, or for instance, for water uptake or for nitrogen uptake. But then, of course, you have only the simulated data, and you can see here that for water uptake, the cereal suppressed the legume in all of the environments according to the model. Whereas if you look at N uptake plus fixation, you can see that in two environments, well, this one is maybe neutral there, but here in one environment, complementarity and cooperation were stronger than the competition, which is the organic side, the low input side. And whereas in that side, you have the high input side, where again the cereal suppresses the legume. So this gives you using the model data, it gives you a bit more information about the competition for different resources. So which ecosystem services are fostered by intercropping? I have 5 minutes left, right? Okay. Now I understand. I understand.
You can take a few more minutes. Huh? You can take a few more minutes if you want.
Yeah, maybe I wanted to ask all of this to you. So the good thing is that I talk so much and you have to talk less. Not sure who profits from that. So we have different ecosystem services to and from agriculture. These are services to agriculture, And this service, negative one, is always in purple. You have water and soil and so on, but also pests and diseases from ecosystems to agriculture. And then we have also the services from agriculture to ecosystem services or the society. Yeah. Key ecosystem services, of course, food, fodder, and fiber, then also carbon sequestration, diversity conservation, recreation. Yeah. And then there are also a bunch of disservices like loss of biodiversity, water pollution, erosion, greenhouse gas emissions, and so on. And I made those in bold letters, which we can usually address with the model. And here I made it, and here I added the farm management tools we have. Farmers have tillage, pest control, genotype choice, and so on, management. And I also made those in bold, which we can also simulate. So we can simulate the effect of the genotype choice, or they can simulate the effect of the fertilization or the crop rotation on these ecosystem services. So to show you the potential applications. Usually we focus on yield, but we can also focus on greenhouse gas emissions or water pollution in terms of nitrogen leaching, for instance. Short examples. So here, what is the effect of management on LER? How can we use models for that? Just to show you the theory or the method. So here we have simulated the PLER in red of bean and in green of wheat for different sowing densities. So 50% of wheat and 40% of faba bean at different ratios, or 50-50, 50-60, 50-70. And then you get a specific PLERs, and you can sum them up to get LER. And now you may wonder why we have always a box plot. So we did that with this calibrated and validated model, and we used the so-called weather generator that uses the weather data of a site. So we have, let's say, 20 years of weather data from the experimental station. We put it in the weather generator, and the weather generator blows up the data. It has then the same statistical characteristics, but you have then 100 years or 1,000 years. Yeah. So you can run then 1,000 years of data and get box plots. You get it's a statistical tool also. And the same you can do also for biased research, such as me with roots. You can differentiate here, or you can test different trait effects. So what would be the effect of if I change the maximum rooting depth of wheat and bean? So wheat the maximum rooting depth could be very shallow one, 84 centimeters, or bean 79 centimeters, or then you have much deeper rooting ones. And interestingly, you see you have the highest LER when you combine a shallow rooting with a deep rooting one, whereas you have the lowest ones if the maximum rooting depth are very close to each other, which makes sense. Of course, this is what we expect. Okay, so then I'll finish in the last 3 minutes. Can we use crop models to find out where and under which conditions intercropping performs well? Maybe this is the overarching question we all have. And to some extent, at least, we can use models to do so. And I will show you some preliminary results we have not yet investigated in detail, but more to show you how it is done. So we have this intercrop model that was for now only used for faba bean and spring wheat. And what we have done is we have soil data from 210 locations of NRW, which is this federal state here in the west of Germany. We have weather data from the German Weather Service of 30 years, 1990 to 2020 or something like that. And we ran the model we have calibrated, but then also we changed the traits. So we changed a bit the height, of course, so plausible heights, of course. And we changed the daily rooting rate or root elongation. We changed the canopy extinction coefficient, and then also we played with the management, so the amount of N fertilizer. So this in the end led to 16,000 combinations of model runs. Then you put it on the high performance computer, go on holidays and come back. And then this is what Senator has done.
And then you found that after day one it crashed. Or...
No, yeah, he waited 2 more days. This is what I told him. Don't do it at the last day. And then he calculated the LER for each year, and then he averaged it over the 30 years. And what you get then, so this is, you cannot see that at all. This is the map of NRW, and these points are the soil points, soil locations, when we have this in-depth information about the soil properties. And it shows, the colors show the LER from red, very high, and well, very high, up to 1.3, and then blue is 1 and a bit below. And but what is interesting is that you have seen it also from Bobke, and the good thing is that the mean LER is now 1.17, which fits exactly, but that's a coincidence. So the mean is 1.7, but then if you play, for instance, with the fertilizer, so this is the baseline where we have baseline cultivar rates and management, and then if you play with the N, so you apply N, and you apply even more N in the scenarios you see. So this is then the mean is 1.16, and here it's 1.11. So you see a decline of the LER if you increase the N input. So this is what you can do with the model. Actually, you can test very many combinations of traits and of management options of choices of species to try to find which performs well under which environment. And I think with this I'm at the end. Yeah. So most of this I've already said. Maybe this one I haven't said. So what we found out, at least in our experiment, is that for farbing the water was most critical resource, whereas for spring bean it was the nitrogen, which is also actually what we would expect. But I'm always happy if the model proves what we already know, because only then we can use it.
Then you can believe it.
Then you can believe it. Exactly. Yeah. So that's it from my side. Thanks for your attention.